Welcome to the next lecture on CISC and RISC architecture. Now, we will be moving on into the architecture. So, till now we have seen till now what we have seen that how an instruction get executed, what kind of instruction format is available, and what kind of addressing modes are used. So, now we will be looking into that architecture where we can divide those sets into some groups, that is RISC and CISC architecture. So, these are broad classification. So, the computer architectures we know that has evolved over the years, and there are many features that were developed for mainframes and for supercomputers in the 1960s and 70s, and that started to appear on a regular basis on the later generation of microprocessors. So, based on that we have so many features. Now, we are dividing those into group of two. They are broadly classified into complex instruction set computer called CISC and reduced instruction set computer called RISC. Now, let us see how CISC and RISC architectures differ. Coming to CISC, it is a more traditional approach is followed here. So, the main features of this complex instruction set computers are they have complex instruction set. The instruction set are not very simple. They also have a large number of addressing modes that we have seen. They also have some special purpose registers and flags that are used to carry out various operations, and the instructions are not all of same length. So, they have variable length instructions. So, as I have already told earlier that if you have a fixed length instruction, it becomes easy for encoding, but if you have variable length instruction, then the encoding needs to be is little complex, and it also takes some more time, because you have to know each of the bit, and based on that a particular action will be performed. So, ease of mapping high level language statement to machine code is possible in CISC, but instruction decoding, control unit design is much more complex. And of course, if you have variable length instruction, pipeline implementation will also be quite complex. We are not saying that it will not be there, it will be there, but it will be complex. Now, CISC machines are in 60s and 70s, we have seen IBM 360, 370, VAX 11 was one of the popular in 70s and 80s, and from 1985 until present is the Intel. So, Intel processor that we use is a CISC architecture, it follows a CISC architecture, and this is the only architecture that is CISC instruction set has survived over the generation. So, over the generation if you see any CISC machine, that is the Intel ones, and the desktop PCs, laptops, we use them. And why that is so? Why this? Why they have to still use the CISC? One thing is backward compatibility. By that what we mean is that they started with some machines, some instructions. Today also those instructions can be executed in the machine, but in the newer machines you have newer features, but still they are backward compatible. And this was also possible because the volume of chips that is manufactured is much high. So, you can see that there is enough motivation to pay this extra cost of the design, although you are paying some extra thing for the CISC architecture. And there are sufficient hardware resources that are available to translate from CISC to RISC internally. So, internally it is getting converted into RISC, but the architecture set, the instruction set architecture is CISC for Intel. So, this is the register set in Pentium. So, here you can see that it does not have a large number of register, although they have got some register. These are code segment, stack segment, data segment, but it does not have a large number of register. Also, this program counter, which we say, they call it instruction pointer, they have some conditional code flags for it, and there are several other registers to perform different kind of jobs. These are the addressing modes that are present in VAX machine. This was a very popular machine in the 80s. So, just see how many addressing, almost all addressing modes are present, starting with register direct, immediate, displacement, register indirect, indexed, direct, memory indirect, auto increment and auto decrement, and scaled. So, the VAX machine included a huge set of addressing modes. Now, coming to reduced instruction set computer. This used, and this is the architecture which is used in most of the computers today. Not only computers, other processors for microcontrollers and other things, this RISC architecture is followed, very widely used among many manufacturers today. This is also referred as load store architecture. So, by load store architecture, we already discussed that only load and store instruction can be used to access the memory, and all other instruction will be operated on register. So, only when memory is required, you have to load it from the memory. Once the data are available, then you have to execute it, and all execution there you will have registers, only registers. The main features are, architecture is very simple for the sake of efficient pipeline. I already discussed very briefly about pipeline, which will be discussed in more detail later, but we must know that this is one of the main motivation of RISC, that the RISC architecture is simple for the sake of pipeline, because through pipeline we have seen that we will get some advantage in instruction execution time. Simple instruction set are used and very few addressing modes are used. It does not support a variety of addressing modes. A limited addressing modes are used in this machine, but it has a large number of general purpose register, and it does not have many special function register. Rather, these general purpose registers are used for special functions. Instruction length and encoding is uniform for easy decoding. See, if you encode the instruction, all the instruction in a specific fashion, then the decoding will be much easier. And compiler assisted scheduling of pipeline for improved performance will be there. You will be seeing this particular feature more in pipeline. So, the popular RISC machine is CDC 6600, which came in 1964. So, RISC is existing since 60s, and this is more now that people have moved to RISC architecture. And ARM microcontroller family is all having RISC. Even the microcontroller family, other microcontroller family of PIC and others also use RISC architecture. So, almost all computers today use RISC based pipeline for efficient implementation, and RISC based computers use compilers to translate into RISC instructions, and CISC based computer use the hardware. They do not use any software or to convert it like compilers, rather they use some hardware to translate those instruction into simpler instruction, that is RISC instructions. So, a comparative study was performed in the year 1991, where a quantitative comparison between VAX 8700, which was a CISC machine, and MIPS M200, a RISC machine, was compared. And what findings they came up is the following. MIPS required execution of about twice the number of instructions as compared to VAX. That means, the number of instructions that are required by RISC machine is much more compared to CISC. So, as CISC is having more complex instructions, so they require less number of instructions, but on the other hand, RISC required some very simple instruction, but more number of those simple instructions are used. There is a parameter that we will be looking little later, cycles per instruction, we call it CPI. So, for each instruction, what is the number of cycles that it requires? For VAX machine, it was about 6 times larger than the MIPS machine. So, ultimately, to say that, let us say one machine VAX, it is taking only 3 instructions to execute, but each instruction is taking more number of cycles to execute, whereas MIPS had 3 times the performance of VAX. So, there is like 6 times larger than MIPS. So, cycles per instruction was about 6 times larger. That is why, in turn, although MIPS was taking more number of instructions, but they were using simpler instructions. So, the performance of MIPS had 3 times the performance of VAX. Also, much less hardware is required to build MIPS as compared to VAX, because VAX was having many complex instruction. For many complex instruction, you need to do complex decoding. So, the hardware requirement is much more, whereas RISC they used simple instructions, although they require more number of instructions. So, in that case, this MIPS becomes 3 times faster than your VAX. So, the conclusion was, persisting with CISC architecture is too costly, both in terms of hardware cost and also performance, and with this VAX was replaced by Alpha, which was a RISC machine. So, they moved from CISC to RISC after such study. So, this was a machine by DEC. So, CISC architecture based on x86 is different. How it is different? Because of huge number of installation base, backward compatibility of the machine code is very important from commercial point of view. So, when they came up x86 series, they were the main persons in the market they were the main sole authority in the market. So, there were many installed base and they require a backward compatibility. So, if backward compatibility is required, you need to have the instructions which you are having earlier, those instructions should run, along with which you can also execute more number of instructions, more other instructions. So, because of such thing, CISC, this x86 which is a CISC machine, it is still very important, and they have adopted a balanced view. How is that balanced view they have adopted? A user view is a CISC instruction set, and there is a hardware which translate every CISC instruction into an equivalent set of RISC instruction internally. So, ultimately internally they are having some kind of RISC instructions, and also this instruction pipeline executes this RISC instructions efficiently. So, they still have this older CISC architecture as a user point at the user point of view level, but at the lower level they have this RISC, where those instructions are converted into simpler instructions and those simpler instructions are executed. Pipeline can also be performed there, which makes it more efficient. Now, we will be going into MIPS 32 architecture. We will be now taking on with MIPS. Till now, we have talked about various kind of architectures. Now, we will be directly moving on with one architecture, which is a RISC architecture, and we will be performing a case study of this MIPS. We will look into the instruction set, instruction encoding in detail, also the design of the data path of MIPS architecture, and we will also look into the control unit design issues in the later units, and we extend the basic data path of MIPS to a pipeline architecture and discuss some of the issues therein. Now, MIPS 32, the CPU register, how many CPU register it is having? This MIPS instruction set architecture, it defines the following CPU registers that are visible to machine or assembly language programmer. So, there is a total of 32-bit general purpose registers starting from R0 to R31. So, there are total of 32 register. There is a special 32-bit program counter, that is PC. What it does? It points to the next instruction in the memory to be fetched or executed. Now, this is not directly visible to the programmer and it is only affected by certain instructions. When it is affected, you think of a branch instruction, you think of a call. When you are going to a branch, then PC must be loaded with the branch address. You have to calculate the branch address with an offset and then you have to go and execute that. Now, a pair of 32-bit special purpose registers are also present. We call it high and low, which are used to hold the result of multiply, divide and multiply accumulate instruction. Now, say when you multiply 2n bit numbers, the result can be 2n bit. So, you need to store it in a 2n bit register. So, for that purpose, we have two 32-bit register, we call it high and low, which are used for this multiply, divide and multiply accumulate instructions. Now, these are some common registers that are not present in your MIPS 32. What are those registers? We do not have any stack pointer. We already know what is a stack pointer, which helps in maintaining the stack in main memory, but we do not have any such kind of stack pointer, any register of such kind in MIPS 32. We do not have any index register as well that can be used for, we have already seen index addressing mode, we require index register for some purposes, but it is not present. And what can be done is that as these are not present, you can use any register from the set of 32 registers and you can use it as an index register. That can be possible. Also, there is no flag register. Now, you can argue that if there is no flag register, then how we will be checking the operation? You have to perform the operation, store it in a register, check that value. This is how you have to check. So, we do not have any flag register like 0, sign, carry and overflow. Now, why we do not have this? You have seen in pipeline, there are different instructions that are coming in and they are going in a pipe. In an overlapped fashion, we are executing those instructions. Let us say, if we have this flag registers, it might happen that one instruction has updated some flag, then the other instruction is, that instruction is not fully executed, and other instruction, as it is in an overlap fashion, some other instruction has updated that flag, then there will be a problem. So, instead of doing so, this flags can be maintained in some other fashions using in this MIPS 32-bit machine. Now, these are the general purpose registers, these are the special purpose register I have already discussed, and R0 register is hardwired to the value 0. So, R0 contains always 0 value, can be used as target register for any instruction whose result is to be discarded. If you want to discard that result, then you store it in R0 such that it will be discarded, or if you want to add a 0 value to some register, you can use R0. R0 is constant, which is 0, set to 0. R31 is used to store the return address when a function call is made, like as I already discussed that there is no stack pointer. So, if there is no stack pointer, when there will be a call, return, branch, these kind of statement, it may affect, you have to store the address of the PC, and then later when again we execute that branch, we will come down to that particular address and we execute it. So, in such case, we can use this R31 as return address, and used by jump and link, that is JAL, and other instruction branch less than ZL and branch greater than ZL, etc., and can also be used as a normal register. If you are not using it for any return value, you can also use that for your normal register. Let us take some examples. So, load R5 50 R3. So, what does this instruction? It load from this particular address, it will add 50 plus R3, then it will go to that particular memory location and load the value to R4. Here R1 plus R4 is added and it is stored in R2. Similarly, storing means we need to store R2 into this particular location, that is 50 plus R3. And this is like what we are doing. There is no move instruction, rather how will you move a data? If you want to move a data from R5 to R3, all you can do is that you can add R5 with R0 and you can store it in R2. So, what happens? R5 is moved to R2. Now, these are some examples, like we have a main code from where our execution starts, and then we have another subroutine. So, what happens here? This is an add immediate, we are adding this immediate value to R0, which is 0. So, R1 will have 35 and R2 will have 56, and this jump instruction will go to a function which is labeled by GCD, and in GCD you will be seeing this some code for your GCD will be written, and jump return. Jump return will do what? See, at this point of the time when you have accessed this particular JL GCD, then the PC value has moved to the next location. Now, what you need to do? Now, after fetching and decoding, you have understood that you have to move there. So, this PC value must be stored in that return address. It can be stored in R31, and then we move to this GCD, we execute that. At the end of GCD, you must have an instruction which is JR, return, jump to return address, where you have to go to R31, get the value, loaded in PC, and then from this point the execution will start after returning back here. Now, how are high and low registers used? As I said, during multiply operation, high and low registers store the product of an integer multiply. HighLow denotes the high order, Hi denotes the high order 32 bits, and this denotes the low order 32 bits. And during multiply add or multiply subtract operation, the high-low registers store the result of an integer multiply add or multiply subtract. And during a division, high-low register store the quotient in low and remainder in high of an integer divide. So, high-low registers are used for these few purposes. Now, let us see little more MIPS 32 assembly language convention. So, the integer registers, as I said, are numbered from R0 to R31, and if you want to code this, I am talking about some assembly language instructions. You can write an assembly language code. So, for doing so, some simulators are available in public domain. So, one of is Qt-Spim, and this Qt-Spim you can write assembly language code there and you can execute it. And these conventions have become a de facto standard when we write an assembly language program for MIPS. So, a Qt-Spim is exactly a MIPS 32 simulator that can be used to write assembly language programs. Basically, some alternative names are used for register to indicate their intended use in this. So, register 0 R0, which is a constant 0. So, register name here which is used is $0, used to represent constant 0 value whenever required in a program. At, this particular register is reserved for an assembler. Okay. It is reserved for an assembler. The name is at, and this may be used as temporary register during macro operation by an assembler. An assembler provides an extension to the MIPS instruction set that are converted to standard MIPS 32 instructions. Let us see an example. Load address instruction into load the address instruction used to initialize the pointer. That means, in R5 what we are doing? We are loading an address. ADDR is a label from where we have stored some data, and I am loading that particular address into R5. But this instruction is not there in your MIPS. So, how MIPS will see this? MIPS will convert this into set of two instructions, LUI, load upper immediate. So, at this upper 16-bit of address is loaded, and then we do an OR immediate. We are doing an OR immediate with the lower 16-bit address. Firstly, I have loaded the 16-bit number in the upper immediate. So, let us take this example that will make it clear. So, see this example what we are doing here. So, this load address is loading this particular address into T1, and this is nothing but ADDR. Okay. Either you write ADDR or actually this address will get loaded in T1. So, this is a 32-bit number. We do not have such kind of address LA in MIPS. So, this instruction will break down into couple of more instruction when you actually execute, and how it will get executed? Load upper immediate. So, this is the upper 4-bit A, B, C and D. So, in $T1 the upper 4-bit is added. So, now you see in T1 this 16-bit is loaded with A, B, C, D. Now, what will we do? We do an OR immediate that will add this and this with T1. In T1 you already having this particular value. You are doing an OR with 0x1234, that is the next 4-bit. You are ORing with 1, 2, 3, 4. You are ORing with this, and after ORing you are storing back the result in T1 itself. So, in T1 you will have A, B, C, D, you have odd with 1, 2, 3, 4, 1, 2, 3, 4. So, this instruction is doing exactly what I explained. Similarly, we have another register, that is V0 and V1. The register that are used is R2 and R3. So, result of a function or an expression evaluation is stored in V0, and in V1 result of a function or for expression evaluation. So, V0, V1 are used for storing the result of a function. Let us see. Maybe it can be used for up to 2 functions, return values, and also as temporary register during expression evaluation. So, when we are using it for this purpose, like result of a function, it can be used, or other time you can use it for expression evaluation. Next set of register is A0, A1, A2, A3, where we use this arguments. So, these are used to pass up to 4 arguments. 4 arguments can be passed to function using the following register name A0, A1, A2 and A3. These are temporary register T0 to T9, and these are not preserved across calls. So, it might happen that when you are using this register for some purpose, it can be also used for other. So, it is not preserved across the call. May be used as temporary variables in programs, but these registers might get modified. So, it is up to you that if you are using this, then you have to be careful enough, and these register might get modified when some functions are called other than user written functions. That means, inside also we are calling some function, some instruction are breaking down into some further instructions. So, in this particular case you can see that it can be user other than user written function, it can be overwritten, but these are preserved across call. So, even if there are some other function call, you can use this set of temporary register starting from S0 to S7. May be used as temporary variables in the program. So, I will suggest you, if you are coding this using, you are writing some assembly language program, then you can use this set of registers for your programming purpose. We have another set which is GP, SP, FP and RA. So, see, we have, this is pointed to global area, GP is pointed to global area, SP is your stack pointer, FP is your frame pointer and this is your return address. So, we are having all these, but we are not having with a special function register. Rather, the general purpose registers are only used for this, but we know that R29 is a general purpose register which is used for stack pointer, which is used as stack pointer. So, these registers are used for variety of pointers. So, global pointers, as I said, point to the memory location from where the global variables are allocated space. Stack pointers, we know that it points to the top of the stack. A frame pointer points to the activation record in stack, and return address is used while returning from a function. We have another register K0 and K1, it is reserved for OS kernel. So, these are highly recommend not to use these registers. So, we came to the end of lecture 8. So, in this lecture, now we have given you an idea that what we will be discussing in next course of time. We have discussed about some properties of instruction set architecture, and now we are moving on with a particular architecture, that is MIPS 32. and I have discussed some of its features and will be discussing many more in course of time. Thank you.